So in this video, we're going to go over the problem we were doing on Friday in class, which is two-dimensional collisions. So we had two clay balls that were going to collide and stick. We had ball one down here, which has an initial velocity perfectly to the right of 3 meters per second, and the mass is 2 kilograms. The second ball is going perfectly up with a velocity of 4 and a mass of 6, and they're going to collide together and they're going to stick. So part B is showing this new collision. We get mass 1 plus mass 2 in this new object. And the two questions that we have: first, what is the final velocity after the collision? So this object here, right, it has some velocity somewhere, probably in the first quadrant, because momentum is going to be conserved, so it's going to be going up and to the right. But we want to know, what is this new velocity, which implies both the magnitude and the direction, right? We need to know at what angle is it going in that first quadrant. Then the second question, which will be addressed in the second video, is what is the impulse felt by each individual object, okay? So, like I said, we are going to be thinking about conservation of momentum, which is true in all cases, right? So we were doing one-dimensional collisions and momentum was conserved. Remember, we now have two dimensions. We are moving both east and west and north and south, and we are going to treat this like we treat anything that has multiple dimensions. We have to separate into the x and the y, okay? That will not change. We've done it for projectile motion. We've done it for forces. We are absolutely going to have to treat the components, right? Break things into components and treat the components differently because the x is different than the y, okay? So what we can do is think about conservation of momentum, which tells us that the momentum before the collision, right, P total naught is going to be equal to the momentum total after the collision. And the thing that we are going to have to stipulate here is that the P total, now we are going to have to think of in the x direction before the collision is going to be equal to the momentum total in the x direction after the collision. And we can say the same thing for the y. And that's what we're going to have to do here. Okay. Again, the subscripts are telling us exactly what we're talking about, the momentum total in the x direction before the collision. So we're going to do that here, and I'm going to be explicit and talk about, right, x and y. And we've seen this, like I said, when we're doing forces, when we're doing projectiles, break it into x and y. So what this means for us, if we're thinking about the x direction first, okay, and we can actually make sure. All right, so our x direction, the first ball is moving perfectly to the right, and the second ball is moving perfectly up. So the second ball has no x momentum. The first ball has only x momentum. So if we think, again, P total x before the collision is going to be P total y after our collision. And there are two objects in this system, and we're going to form one object on the other side. So the total momentum before, we're going to look at, right, the momentum of the first object in the x direction before the collision, plus the momentum of the second object in the x direction before the collision, is going to be equal to the momentum of that entire object, which we will call P1 plus P2, right, because there's only one object after the collision, in the x direction after the collision. Okay, and remember, we find momentum by mass times velocity. So for our first object, its mass is 2, its velocity, again, we're talking about the x direction, all this velocity is in the x direction. So we would do 2 kilograms times 3 meters per second, and that's the first object. We said the second object has no velocity in the x direction because it's moving perfectly north, right? So if we want to be explicit about what's going on, the mass technically is 6, but it has no velocity in the x direction. And that's going to be equal to the momentum of this new object, whose mass is 1 plus 2, right? The mass is, right, 2 plus 6 kilograms. times whatever its final velocity is. And the reason why we're doing this, I should have been a little bit more explicit, right? We're looking for the final velocity. So in momentums, we know that we have initial velocities and final velocities. So it is this piece right here that is going to give us the x component of the final velocity, and then we can find the y component of the final velocity and put those two together. So we have 6 plus 0 is equal to 8 times final velocity of x. So phi fx is going to be 0.75 meters per second. Okay, so that means that this new object is going to be traveling with a velocity in the x direction of 0.75 meters per second. Okay, but that's not the only thing, because there's going to be some y velocity, and we're going to do the same thing, just thinking about the y direction now. So p total y naught is going to be equal to p total y final, and I just realized that over here I accidentally wrote y when it should have been an x. Sorry about that. So our momentum of object 1 in the y direction before the collision plus the momentum of object 2 in the y direction before the collision should be equal to the momentum of that new object formed in the y direction after the collision. Okay, so we talked about how object 1, all of its momentum is in the, all of its velocity is in the x direction, so its momentum was in the x direction. We're going to see we have 2 kilograms but no velocity in the y direction, plus our second object, all of the velocities in the y direction, so all of the momentum's there. 6 kilograms times 4 meters per second is going to be equal to, again, we have this new mass of 6 plus 2 times some final velocity in the y direction. So we're mirroring the same thing that we had in the x. So we have 0 plus 24 equals 8 VFY, and this comes out to 3. You get VFY equals 3 meters per second. So this object also has a velocity in the y direction of positive 3 meters per second. We said that is the VFY. And remember, these have directionality to it, so this object is moving, still has a velocity of north 3 meters per second and east 0.75. So it is important when we're dealing with our vectors to pay attention to the sign. So if we want to answer this question, which says what is the velocity after the collision, well, we found the components. We now need to put them together and find, right, our hypotenuse of these two. So to find VF total, we are going to do the square root of 3 squared plus 0.75 squared. Right, we're just doing Pythagorean theorem. So it's like 3.09, but I just want to make sure. 3 squared plus 0.75 squared. Yep. VF total is equal to 3.09 meters per second. But this is not it. We found the magnitude. We now also need to find the direction. So we need to find theta. And we're going to use tangent of the angle is equal to opposite over adjacent. And we're looking for theta. So we need to do inverse tangent of opposite over adjacent, which gives us, right, opposite here is the 3 meters per second, and the 0.75 is the adjacent. So we're going to do inverse tangent. Nope, that's A2, right? Yep. Tangent 3 divided by 0.75. And this gives us an angle of 75.96. So I'm just going to round that to 76 degrees. So our final answer for this first question is 0.39. Our final velocity is 3.09 meters per second at 76 degrees, and I don't have to give a directionality to it because we know that by convention in geometry, 76 degrees is going north from the east axis. So 76 degrees, you don't have to give a northeast or anything like that. So that's our answer for the final velocity. I'll have a second video that shows how we get the impulse